Okay, good. Oh, wow. Um, Section 12.4, the cross product. So I will define the cross product as, well, in the cross product, I'll need two vectors in R3. And so suppose I have a vector A with components A1, A2, A3, and a vector B with components B1, B2, B3. Then I'll define the cross product of A cross B as, well, having component A2B3 minus A3B2. Second component, A3B1 minus A1B3. Third component, A1B2 minus A2B1. So you can think of this as sort of an analogy that this can be thought of as sort of the determinant of, well, in the first row, it'll be the vectors I, j, and k. Second row will be the components of A, and the third row, the components of B. And then this would give you the same sort of definition. Or you can think of, well, put down 1, 2, 3. Then it would just be, well, you start with 1. So the first component will be 2, 3. So it's going to be A2 times B3, then go in the opposite direction, minus A3 B2. Then the second component would be 3, 1. So A3 B1 minus B3 A1. Next component, 2, 3. I'm sorry, 1, 2. And so it would be A1 B2 minus B2 B1 A2. And that is the cross product. So however you memorize it is how it's done. So this has something to do with the geometry of space, and so that's why this trick here works. Okay, so the geometry of R3. So let me give you a theorem. The vector A cross B is orthogonal to both the vector A and to the vector B. So let's prove this. So first, I guess let's prove that it's orthogonal to the vector A. So let's look at A cross B. I want to show it's orthogonal to A. So let's take this dot product and see that its dot product is 0. And so I have here A cross B is A2 B3 minus A3 B2, comma, A3 B1 minus A1 B3, comma, A1 B2 minus A2 B1. I will dot that with A1, comma, A2, comma, A3. So this should equal, well, let's multiply this first component here by A1. So it's A1, A2, B3 minus A1, A3, B2 plus, let's multiply the second one by A2. So it's A2, A3, B1 minus A1, A2, B3, plus, multiply this last one by A3. So it's A1, A3, B2, minus A2, A3, B1. And so, this is equal to, well, let's see, A1, A2, B3, oops, 1 second, I forgot something here. This is, I multiply everything by that, so it's B1. Okay, so let's cancel. A1, A2, B3 cancels. A1, A3, B2 cancels. A2, A3, B1 cancels. So you get 0. Okay, so that's what I want to show, that A was orthogonal to the cross product. Let's show that B is also orthogonal. So let's do A cross B dot B. Okay, so this is equal to, well, like above, A2, B3 minus A3, B2, comma, A3, B1 minus A1, B3, comma, A1, B2 minus A2, B1 dot B1, comma, B2, comma, B3. Okay, 1 second. Okay, so let's multiply this. So this is equal to A2, B1, B3 minus A3, B1, B2 plus A3, B1, B2 minus, that's a B1, A1, B2, B3 plus A1, B2, B3 minus A2, B1, B3. Okay, so let's see what cancels. A2, B1, B3 cancels. A1, B2, B3 cancels. A3, B1, B2 cancels. And so you get 0. And that's what I wanted to show. So I've shown that both A and B are orthogonal to A cross B. Okay, next theorem. We have shown that A dot B is just equal to the norm of A times the norm of B times cosine of theta. Well, I'll show that analogously, that similarly, not analogously, but similarly, the norm of A cross B is just the norm of A times the norm of B times sine of theta. Okay, so let's show this. So I have here A cross B, and let's dot it with itself. And so A cross B A2, B3, A3, B2, comma, A3, B1 minus A1, B3, comma. A1, B2. Okay, start over. A1, B2 minus A2, B1 dot, same thing. Hopefully I can, these are equal. A2, B3 minus A3, B2, A3, B1 minus A1, B3, A1, B2 minus A2, B1. Okay, so these are equal. So this is equal to A2, B3 minus A3, B2 squared plus A3, B1 minus A1, B3 squared plus A1, B2 minus A2, B1 squared. So now by the special product formula, this is equal to A2 squared, B3 squared, minus 2, A2, A3, B2, B3, plus A3 squared, B2 squared, plus. Okay, now let's square the second one. So it's A3 squared, B1 squared, minus 2, A1, A3, B1, B3, plus A1 squared, B3 squared, plus, okay, lastly, let's square this last term. So by the special product, this is A1 squared, B2 squared, minus 2, A1, A2, B1, B2, plus A2 squared, B2 squared. Okay, just had enough room. So this is equal to, I guess let's sort of order these as best I can. So let's do A1 squared, B2 squared, plus A1 squared, B3 squared, plus A2 squared, B1 squared, plus A2 squared, B3 squared, plus A3 squared, B1 squared, plus A3 squared, B2 squared, let's do the minuses. Minus 2, A1, A2, B1, B2, minus 2, A1, A3, B1, B3, and then just one more. Minus 2, A2, A3, B2, B3. Okay, so 2. So let's see how many terms, if I have the correct number of terms at least. Okay, so 2, 4, 6, 8, 9. 2, 4, 6, 8, 9. Okay, good. And that will be 369. Yes, okay. So I haven't forgotten any terms at least. So I can write this as oh, I'm missing some terms here. So let's write this as a1 squared b1 squared. I'm going to have to subtract off that term. Plus a1 squared b2 squared. Plus a1 squared b3 squared. Plus a2 squared b1 squared. Plus, I'm missing this term, a2 squared b2 squared. Plus a2 squared b3 squared. That's a 2's, okay. Plus a sub 3 squared b sub 1 squared plus a sub 3 squared b sub 2 squared. And then I'm going to have to add this term, a3 squared plus b3 squared. Okay, so I added those, and I guess I'll have to subtract those off. So all of the diagonal terms, I had to add those. So I'm going to have to subtract them off. Oops. So I'm subtracting off these 3 diagonal terms that I added. And I still had those, these last 3 terms. Minus, sorry about this. Let's see if I can get control back. Minus 2 a1 a2 b1 b2 minus 2 a1 a3 b1 b3 minus 2 a2 a3 b2 b3. Okay, good. So this is going to equal, well, a1 squared plus a2 squared plus a3 squared times b1 squared plus b2 squared plus b sub 3 squared. Okay, so if I look at that, I multiply each of these by a1 squared, that's this, each of these terms by a2 squared, that's that, and each of these terms here by a3 squared. So that's that. So that's this first, oh, that 3 almost looks like a comma. It's, okay, good, that looks better. So that's his first line. Minus, well, it's other stuff. So minus this stuff here. A1 squared, B1 squared, A2 squared, B2 squared, A3 squared, B3 squared, plus 2A1, A2, B1, B2, plus 2A1, A3, B1, B3, plus 2A2, A3, B2, B3. Okay, good. So I have this first product, a1 squared, a2 squared, a sub 3 squared, times b sub 1 squared, b sub 2 squared, b sub 3 squared, minus, okay, so now I'm going to have to write it somehow. So let's write it this way. So let's write this. A1 squared B1 squared is A1 B1 A1 B1. The next one. Okay, so I have here an A1 from this term, an A1 A2. Let's write it this way. Let's write it as A1 B1 A1 B1, and then A2 B2 plus, okay, well, now I have here an A1 B1. So let's do that term. So I have plus an A1 B1 times A3 B3. Okay, so I factored out the A1 B1s, and those are remaining. Okay, so that was this term. Now let's do the next one. So plus that's a 2, so let's try to get a 1. Okay, so plus A2 B2 A1 B1 so that's an A2 B1 and an A1. So it's an A2 B2 and an A1 B1. Okay, good. So I've gotten rid of this term and this term, got rid of parts of the other ones. So plus, let's write this guy here as A2 B2 A2 B2. So I've gotten rid of these terms here and this term, plus, so I need an A2 B2 A2 B2. So I have here an A2 B2, and what remains is A3 B3 times A3 B3. Okay, good. So that's part of this term here. Plus, so I got A1, so now let's do a A3 B3. So plus A3 B3. So let's see an A3 B3. Okay. And what remains here is an A1 B1. So that gets rid of this term. Plus, let's do an A3 B3 and an A2 B2. So that gets rid of this term. So this plus this is that, which got rid of that. And then this plus this got rid of that term. Okay. And now let's see, plus A3 B3 A3 B3. And this term, get rid of that term. And so I've collected all my terms. So I've written these 1, 2, 3, 4, 5, 6 terms as 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. 1, 2, 3, 4, 5, 6, 7, 9 terms. Good. So I've just rewritten these. So now, let's do this some more. So this is equal to a1 squared plus a2 squared plus a3 squared, b1 squared plus b2 squared plus b3 squared. So that's just this first product. Minus. Okay, so now let's rewrite this. I can factor out a1, b1 times, that's probably too much space, but times a1, b1 plus a2, b2 plus a3, b3. Okay, so that's these first three terms. And now plus a2, b2 which gives me, so this a2, b2 times these, well, that's a2, b2 times this first term, a1, b1, times a2, b2 times a3, b3. Good. Plus, so let's factor out the a3, b3. And so I factored out the a3, b3 times a1, b1, a2, b2, and a3, b3. So this is equal to well, this term here just looks like the dot product of a vector with itself This looks like the dot product of a vector with itself. This just looks like, well, this term is the same as that term. So it just looks like A dot B squared. So this just looks like A dot B, and they're the same, so it's squared. Well, the A dot A is just the norm of A squared. B dot B is just the norm of B squared. And A dot B, well, we know that that is just the norm of A times the norm of B times cosine of theta. Okay, so this is equal to the norm of A squared times the norm of B squared minus, well, the norm of A squared, the norm of B squared, cosine squared theta. I can factor out the norm of A squared. The norm of B squared. And what I get is 1 minus cosine squared theta. And so this is just the norm of A squared times the norm of B squared. And 1 minus cosine squared is sine squared. So therefore, I get that A cross B is just equal to taking the square root of, well, that's long, taking the square root of both sides of my equation. Stop. Will you stop? Just stop for 1 second. Stop. Stop. Okay. Okay, now let's go in the opposite direction. So I can go up a little bit more. See where I was at before it started to have its mind of its own. Okay, so this is just equal to the norm of A times the norm of B times, well, the absolute value of sine of theta. And so, if I assume that theta is such that the sine is always positive, or non-negative. Let me restate that. So that the sign is never negative. Then absolute A cross B, the norm of A cross B is just the norm of A times the norm of B times sine of theta. And that's what I wanted to show. Okay. Next, I have the following corollary, that if neither A nor B is the zero vector, then A is parallel to B if and only if the cross product of A and B is 0. Okay, so let's show that. So, well, two vectors will be parallel if and only if the angle of intersection between those two angles, let me assume that the angle of intersection, for the angle of intersection, I'll take the smallest angle. So the minimum angle between the intersection of those two vectors. And so I'll do that. The angle that's between, let's say, 0 and pi, that you know, where these two vectors intersect. Okay, so then two vectors will be parallel if only if their angle of intersection is either 0 or pi. Okay. And so, in either case, the sine of theta is 0. Since the sine of theta is 0, then the product of norm of A, norm of B times the sine of theta will be 0. And by the above, I've shown that this product here is just A cross B. And so, well, of course, the only way that a vector can have a norm of 0 is if it's 0. And so I've shown that A cross B is the 0 vector. And that is what I wanted to show. Okay, so note the following. The length of A cross B, the norm of A cross B, is the area of the parallelogram determined by the vectors A and B. Notice the following strange relationship between I, J, and K. So, I cross J is K, I cross J is K, J cross I is minus K, so J cross I, notice going the opposite direction, so J cross I is minus K, J cross K, so J cross K is I, and K cross J, going the opposite direction, is minus I. And K cross I is J, and I cross K is, again, going across the opposite the arrow, minus J. So you can look at the above diagram, and it tells you the relationship between of the cross product of the standard bases. And so to determine the properties, the values of the cross product, you can just look here at this diagram. Okay. So the cross product, as I've said sort of before, that it more or less is analogous to sort of a multiplication, but it's not a multiplication that we're used to, it's more comfortable with. It's a multiplication that doesn't have many of the properties that you think multiplication should have. So the cross product is not commutative. So notice that I cross J is not the same as J cross I. It's equal to its opposite. And so if you do I cross J and J cross I, you get actually the opposite, the negative of the value. Okay. Next, it's not associative either. So you can't change the order, nor can you regroup. So the cross product is not associative. So if I look at J cross K, so J cross K, that gives me I, cross J, that gives me K. Then look at K cross J, so that's K cross J, which is a minus I. And then look at I cross a J cross minus I. So J cross I will give you a minus K. And so this will give you a positive K on one side, and I forget what I said. Okay, actually I should write it down what I get, or I'll forget. So J cross I, J cross K is I, cross J is K. So on this side I get K, and then K cross J is minus I. And then J cross I. Oh wait, did I do it wrong? That gives you a plus K also. K cross J is minus I. And then, so that's a minus I. Okay, and then J cross minus I is a plus K. Well, Hmm. It is non. It is non-associative. I guess this one doesn't work. Okay, so let's try something else. So that one doesn't work. Let's try something. Say something else that does work. IJ. Let's see if this works. I cross J cross K. And do I cross J cross K. Let's see if this works. If not, something works. Um, it's not associative, is what I do know. Um, Let me see here 1 second. Okay, so this is going to be I cross J, which is K, cross K, which is 0, and J cross K is I. That'll give you 0 too. Okay, so let's not do that one. Okay, 1 second. Let's do. I'm trying to think of a different example. And hopefully that one will work. 1 second. If not, I'll have to do it. Okay, let's try. Okay, let's try this. Oh. So let's suppose this. Let's do this. So let me assume that A cross B is not 0. Okay, let's try that. Then let's do, because then I'll get a 0. And assume that A and B are not 0. Well, they have to be, so the cross product. Then A cross A cross B, A cross A cross B. This will work. So this will work actually. Let's do that. Yeah, this will work. A cross B, okay. A cross A is going to be 0. Cross B will be 0. So this side is going to equal 0. Okay. Now, A is perpendicular to A cross B. So the only way that this could be 0 is if one of them were 0, but the assumption is that they weren't 0. And so I know that this is not 0. And so that's a contradiction. Okay, properties cross product. Okay, so I guess my original sort of example that I gave was wrong. So this is 0. I guess I have to do something that wasn't perpendicular. Otherwise, it did work. Okay. Properties of cross product. So first off, suppose that A is in some vector space, and B is in some vector space, and C is in some vector space, and D is in the scalar field. Then, of course, in this case, these have to be in R3 in order for this to work. So these have to be, so these are vectors in R3 in order for you to have a cross product. So maybe I should just say R3. So let's just do R3. Whoops. So these are vectors in R3. And maybe this is some real. Okay, so then A cross B is minus B cross A. So I have that the cross product is not commutative, it's anti-commutative. So it changes its sign when you change the order. Next, dA cross B is just the same as taking out the D times A cross B, which is the same as A cross dB. Next, at least multiplication, the cross product distributes over vector addition. So A cross B plus C is A cross B plus A cross C. And again, the cross product distributes over vector addition. So A plus B cross C is the same as A cross C plus B cross C. Next, we can sort of associate the cross product and the dot product, more or less. So A dot B cross C is the same as A cross B dot C. And lastly, I can rewrite A cross B cross C as A dot C times B, the vector B, minus A dot B times the vector C. Okay, so let's show each of these. So proof of the first one. So I have A cross B is just I, J, K, A1, A2, A3, B1, B2, B3 by the properties of determinants. This is equal to minus I, J, K, B1, B2, B3, A1, A2, A3. So if you have a determinant and you interchange rows, or columns actually, then you change the sign of the determinant. So this is equal to minus B cross A. And that's what I wanted to show. Let me show the second one. that you can distribute that that you can put the scalar multiplication either times any of those two vectors or outside the cross product. So I have that. It's a D A cross B. This is just equal to I J K. So this is DA1 DA2 DA3 B1 B2 B3. So this is the same as I can take the D outside by the properties of determinants. If you have a multiple of one row or column, then you can just take that constant out in front and distribute it or factor it away from either your row or column. And so this is I J K A1 A2 A3 B1 B2 B3. And so this is just D A cross B. So that was the first, well, one of the things we wanted to prove. It's the first expression is equal to the third expression. Now let's show that it's also equal to the second expression. Well, again, by the properties of determinant, this is the same as I J K A1 A2 A3 DB1 DB2 DB3. And so this is the same as A cross DB. And that's what I wanted to show. Okay. Third. I want to show that that the cross product distributes over vector addition. So let's show that. So A cross B plus C. This is the same as A so let's do I J K. So I have an A here, so it's A1, A2, A3. This is a B plus C, and so to add two vectors, you just add their components. So the components of this sum is just B1 plus C1, B2 plus C2, and B3 plus C3. By the properties of determinants, this is the same as if you have a row or column, you can take out another vector from it, uh, and then that becomes the sum of the two determinants. So this is the same as I, J, K, A1, A2, A3, B1, B2, B3, plus I, J, K, A1, A2, A3 of, well, this would be C1, C2, C3. And so this is equal to, so let's write this first term. So this is A cross B. And let's write the second term. So this is A cross C. And that's what you wanted to show. Okay. So let's do the fourth one. Oh, there's no way I can do that. Okay, so proof of the fourth one. So I want to show that, well, again, that the cross product distributes over vector addition. So this is equal to, so I, J, K. So this is A. Again, the sum of two vectors is just the vector where the components are the sum of the components of those two vectors. And so this is A1 plus B1, A2 plus B2, A sub 3 plus B sub 3. And this will be a C1, C2, C3. Just like before, the previous proof, well, by the properties of determinants, this is just I, J, K, A1, A2, A3, C1, C2, C3, plus the determinant I, J, K, with components, so that's B1, B2, B3, C1, C2, C3. And so this is equal to A cross C plus B cross C. And that's what you wanted to show. So that's for the fourth one. Okay, so let's do the fifth one. So I want that A dot B cross C. Oops, I want to show that that's the same as A cross B dot C. So this is equal to, let's write it this way, A1, I. So let's write the vector A, in this form. A2 as the sum of its the product of its components with the standard basis. A2j plus A3k and then I'm going to be dotting that with the following vector. I, J, K. And this would be B1, B2, B3, C1, C2, C3. And so this is equal to maybe I'll write it this way as A1, A2, A3 dot. Okay, so it's 1, 2, 3. Okay, so you start with 1, so it's 2, 3. So B2, C3 minus B3, C2. And then the 2 would be 3, 1, B3, C1 minus B1, C3. And then lastly, it's a 1, 2. So B1, C2 minus B2, C1. Okay, so now let's multiply these together. And so I get A1, B2, C3 minus A1, B3, C2 plus A2, B3, C1 minus A2, B1, C3 plus A3, B1, C2 minus A3, B2, C1. Okay, so this is equal to let's do C1 first. Okay, so C1, so it'll be A2, B3 minus A3, B2, which is good. That looks like a cross product. Plus, let's do a C2. So A3, B1 minus A1, B3 times C2. And then let's do the C3. So A1, B2 minus B2, A2, B1, C3. So this is equal to A2, B3 minus A3, B2, A3, B1 minus A1, B3, and A1, B2 minus A2, B1 dot C1, C2, C3. Okay. So this is, well, the cross product of A1, A2, A3 B1, B2, B3, dot C. Actually, since I wrote in components, let's write it. C1, C2, C3. So this is equal to A cross B dot C. And that's what you wanted to show. I believe that's 5. Okay. And then lastly is that, that weird formula. Okay, 6. Okay. So, let's look at this. A dot C times B minus A dot B times C. So this is A dot B A dot C, which is A1 C1 plus A2 C2 plus A3 C3 times the vector B1 B2 B3 minus A dot B A1 B1 A2 B2 A3 B3 times C1 C2 C3. Okay. So this is equal to, and maybe I'll write it in terms of standard. Well, no, maybe I'll write it this way. So this is A1 B1 C1 plus A2 B1 C2 plus A3 B1 C3. That's this first component here. Let's do this first component here. Minus A1 B1 C1 A2 B2 C3 A3 B3. Now this is the first component. I messed up. That's a C1. This is the first component, so this is all times C1. A1 B1 C1, A2 B2 C1, and A3 B3 C1. Now this is the second component, so I'll just go for the second line. So it will be A1 B2 C1 plus A2 B2 C2 plus A3 B2 C3 minus the second component A1 B1 C2 A2 B2 C2 minus A3 B3 C2 and the third component. So now let's do the third component. So multiply everything by B3. Oh, come on. One second until I get control. Okay, so this is A1, multiply everything by B3. A1, B3, C1. A2, B3, C2. A3, B3, C3. Next, multiply everything by C3. Minus A1, B1, C3. A2, B2, C3. A3, B3, C3. Okay, good. So this is equal to, let me get rid of some things that are the same. Oh, these are the same. That's it. These are the same. And these are the same. Okay, so this is equal to there's an A2 there. So this is A2 times B1 C2 minus B1 C2 minus B2 C1. Okay, that's good. Next, let's do the A3 minus A3 B3 C1, so that's this term, minus B1 C3. I'm still going to skip lines. Okay, so I can keep track of everything. Okay, minus, okay, that's 2 and 3. Let's do, so that's get rid of the first. Now let's get rid of the second. So, second, so 3. Yeah, let's do an A3. B2, C3, minus B3, C2. So minus, that's got to get a 2, A sub 2. And so, no, A sub 1. I'm at the second one, so I skipped 2. It's A1. Okay, so that's got to be a B2, C1, minus, I'm getting rid of that, B1, C2. Okay, so I skip 1, 2, 3, so I want a 1 and a 2. Okay, so A1, B3, C1, minus B1, C3. Okay, so now this one. A2, that's a B2, C3, minus B3, C2. Okay, good. Okay, so this is equal to. See if there's an easier way to do this. So this is equal to, you can do this. So this is a cross product there. Okay, so okay, so let's write this as I, J, K, of, that would be A1, A2, A3, okay, and then that's going to be these components. Okay, so B2, let me give more room. Let me do more room here. So this is going to be B2C3 minus B3 C2. Oh, darn. And then that's going to be an A1 I. And then I have a J. Okay. So that's going to be B3 C1 minus B1 C3, and then I have here a K. A3. And so that's B1, B2, C2 minus B2, C1. Okay. So if I look here, Stop. You stop. Okay. So if I look here, so I do, let's see, 1, 2, 3. Okay, so I do 2, 3. So it would be this times this, which is that, minus this times that, which is this term. Good. So now for the second component is 3, 1. So it'd be this times this, which it is, minus this times that, which is that term. And then 3 is 1 and 2. So it'll be this times this, minus this times that. Good. So that's correct. And, well, this is the cross product of A cross something with these components, B2 C3 minus B3 C2 B3 C1 minus B1 C3 B1 C2 minus B2 C1. But if I look at that, 2, 3. So that's B2C3 minus B3C2. Go to the second one, that's 3, 1. So it's B3C1 minus B1C3. And then go the third one, so it's 1, 2. B1C1 minus B2C2. So this is just B cross C. Okay. Good. And that's what you wanted to show. So you wanted to show that that's what this is equal to. And so that finishes off property 6. Let me stop. Okay. I guess I proved it in less steps. Okay, so the triple product. So the triple product is just defined as A dot B cross C, which turns out to be this. Well, actually, let me do that. Since I have a little bit of room, maybe I can show this. Okay, so let me just show that. So this is equal to B cross C, so this is A, B2C3 minus A1, B3C2 plus A2, B3, maybe I should, no, I won't have room anyway. It's right up here. It's equal to so I'm multiplying by A2 minus, oops, didn't finish that, minus A2 B1 C3 plus, no, multiply by A3 B1 C2 minus A3 B2 C1. So this is just equal to A1, A2, A3, B1, B2, B3, C1, C2, C3. Because, well, let's see. Well, actually, so this is, I guess I should have written in a different order, but it doesn't matter. So this is A1, B2, C3, so that's that first term, plus A2, B3, C1, this term, plus A3, B1, C2, that term, minus this term, A3, B2, C1, which is this term, minus A1, B3, C2, this term, minus the last term, which is A2, B1, C3, this term. And so these are the same. And so we have what's called the triple product. Okay. Actually, maybe I'll maybe I'll just put that here. This is equal to, so that A dot B cross C. Don't have exactly filled up my space. Okay, so notice that these are the same. Oh, I see. I should have. 1 second. Let me correct this little glitch in logic. Okay, there. Okay, so the triple product is defined as A dot B cross C, which is just this determinant. Why do we care? Well, first, note the following. The area of the parallelogram determined by the vectors A and the vectors B is just the norm of the vector A cross B. The area of a triangle determined by the vectors A and B is just half of the norm of A cross B. And this is what we wanted, which was the volume of a parallelepiped determined by the vectors A, B, and C. So if you look at this parallelepiped, this box determined by the vectors A, B, and C, then the volume of it is just the absolute value of this triple product. Okay. The torque in physics is defined as the cross product of the position vector times the force vector. So if you have some wrench or something that you're twisting, and from some point, so that position vector is positioned where it's starting. Its initial point is where you are. That's the point at which you're rotating. Then the torque is defined as that cross product. It's going to be perpendicular to those two vectors. Okay, so let's do some problems. On page 861, find the cross product A cross B and verify that it is orthogonal to both A and to B. Okay, so let's find the cross product. So A cross B is the following vector. So it's I, J, K, and so it's 1/2, 1/3, 1/4, and 1, 2, minus 3. Okay. So let's write this as 1, 2, 3. Okay, so let's do this. So this is equal to 2, 3 So 1/3 times negative 3 is, well, maybe I'll just write it out. So it's 1/3 times negative 3 minus 2 times 1/4. And then it goes, so that's a second, so it's 3/1. So 3/1, 1/4 times 1 minus 1/2 times negative 3. And then lastly I go 1, 2. So 2 times 1/2 minus 1 times 1/3. Okay, so this is equal to 1, negative 1 minus 1/2 is negative 3/2. 1/4 plus 3/2 is, so 1/4 plus 6/2 is 7. 1/4 plus 7/2 plus 6/2, 6/4. Okay, let's try this again. 1/4 minus, so that's 1/4 plus 3/2, same as 1/4 plus 6/4 is 7/4. Okay. 1 minus 1/3 is 2/3. Find the cross product. Okay, done. So this is the cross product. And verify it's orthogonal. So now let's verify that this is orthogonal to both A and B. I don't care where I do it, so let's say A dot A cross B. So this is the same as A 1/2, 1/3, 1/4, negative 3/2, 7/4, 2/3. So this is equal to negative, so 1/2, negative 3/2, plus 1/3, 7/4, plus 1/4, 2/3. Let's write everything over 12. I want to write everything over 12. Minus 9 over 12. 7 over 12. 2 over 12. And so this is 0. So it's perpendicular. Good. Now let's try to show that it's also perpendicular to B. So let's do B dot A cross B. What's B? B is 1, 2, 3. And negative 3/2, 7/4, 2/3. Okay. So this is equal to 1 times negative 3/2 plus 2 times 7/4 plus negative 3 times 2/3. Okay, so this is equal to negative 3/2 plus 7/2 minus 2, so let's say minus 4 halves. And so this is equal to 0. So I've shown also that this is perpendicular. And that's what I wanted to show. Okay. So in exercises 29 through 32, part A. Find a non-zero vector orthogonal to the plane through the points P, Q, and R. And then part B, find the area of the triangle PQR. Okay, so let's do that. So let's first find a vector that's orthogonal to this plane. Okay, so let's find a point in the plane, a vector in the plane. So let's just, subtract. Let's go from P to Q. And so 4 minus 0, 1 minus a negative 2, negative 2 minus 0. That's one vector, the vector joining the point P and Q. And let's do another vector in the plane. Let's say the vector B, let's say from Q to R. And so 5 minus 4, 1. 3 minus 1, 2. 1 minus a negative 2, 3. So 1, 2, 3. So now to find so that's two vectors in the plane. Let's try to find a vector that's perpendicular to these. And so let's just take its cross product. So if I take the cross product, I'll get a third vector, which is perpendicular to those two vectors. Since those two vectors were in the plane, then this vector that I will find will be perpendicular to the plane. Okay, so let's do that. So, oh God, there it is. So this is just I, J, K, 4, 3, negative 2, 1, 2, 3. Okay, so again, let's do 1, 2, 3. So this is equal to. Okay, so I'll do 2, 3. So 2, 3. So 9 minus a negative 4. 13. And then do 3, 1. Negative 2. Minus 12. Oops. I'm in the wrong location. That'll give me a negative 14. And then lastly, this is going to be a 1, 2. So 8 minus 3. 5. And so that is a vector that is perpendicular, orthogonal to the plane. Okay. And I forgot. And find the area of the triangle. Oh, so let's find the area of this triangle. So that was part A. Let me do part B. Okay, so the area of the triangle determined by the vectors A and B, it's just going to be, well, half of this norm. And so let's figure out the norm, which is 13 squared, plus 14 squared, plus 5 squared. Okay. So this is equal to 169 plus 196 plus 25, which is 390. And that's, and you really can't simplify that anymore. And so that's your area. In exercises 33 through 34, find the volume of the parallelepiped determined by the vectors A, B, and C. Okay, so the volume will just be the absolute value of A dot, this triple product, B cross C. No, I don't know how to. So it's the absolute value of this determinant. So maybe I'll say it that way. The absolute value of the determinant, horrible notation, of A 1, 1, 0, B 0, 1, 1, C 1, 1, 1. And so let's do 1, 2, 3. And so this is equal to you multiply 2 and 3. And so it's going to be 1 maybe I should do it. So it's going to be 1 plus. Let's multiply this one. 1 times 1 times 1 is another 1 plus. Let's multiply this. So 0 times 0 times 1 minus. Now let's go the other way. 1 second. Get control back of my screen. Okay, minus 1, 1, 0 minus 1, 1, 1. So it's 1, 1, 1 minus 1, 0, 1. So this is equal to, maybe I'll put the equals out here because it looks confusing. So that's equal to 1 plus 1 minus 0 minus 0 minus 1 minus 0. Okay, so that's just equal to 1. So the volume of this parallelepiped is 1. And that's it. And so that's it for today. And I guess I'll see you tomorrow.